The introduction of the Rover 75 is a significant moment in the history of the Rover brand, as we believe it will change how people see us. Rover are well known for building stylish, elegant and classic cars. The Rover 75's design, coupled with its superb engineering, give this car the substance required to pass Rover's revised and most stringent quality standards. Of course, it's the customer that is the ultimate test. This new car takes the stress out of driving and puts the pleasure back into motoring, allowing our customers to indulge themselves in an inspirational experience. This program, for technicians, is split into 7 sections, and we recommend that to help you absorb the information, it's perhaps best to watch only a couple of sections at a time. Section 1 looks at some general information and new features. Section 2 gives an overview of the new electrical and immobilization systems. In Section 3, we'll discuss the instrument pack, and then Section 4 covers the supplementary restraint systems. Section 5 looks at the engine options, and Section 6, the braking system. Finally, in Section 7, we look at the suspension and steering. In addition, there'll be further videos to explain the engines and engine management systems, the electrical system, and the satellite navigation system. The Rover 75 has been developed as an executive vehicle to replace the Rover 600 and 800. With generous dimensions both inside and out, customers can choose one of 4 engines with a 5-speed manual or a 5-speed automatic gearbox. There are 3 basic comfort levels, which are further enhanced by a large variety of paint colours and upholstery, factory-fitted options and option packs, and numerous after-sales accessories. Rover's operation at Cowley now proudly calls itself Rover Oxford. It's more than just a new name, it's a new factory constructed within the existing buildings. Representing an investment of £700 million, it's yet another measure of Rover Group's continued commitment to quality. Many innovative features are available, such as a rear parking aid, which alerts the driver to obstacles up to 1.5 metres away. Once the obstruction is only 35 centimetres away, the beeps become constant, indicating the need to stop. An optional rain sensor controls the frequency of the intermittent windscreen wipe cycle by continually measuring the quantity of light reflecting from the glass. When the windscreen becomes wet, less reflected light is detected and the wipers are activated. The system automatically compensates for dirt, smears due to worn wiper blades, and windscreen cracks or chips, and its sensitivity is adjusted using the thumb wheel potentiometer on the wiper stalk. The sensor also has its own heating element to defrost or demist its mounting area. A new control unit known as the Light Switch Module, or LSM, controls all the exterior lighting, headlamp levelling, and the instrument panel illumination. It's located on the dashboard and consists of an ECU and a switch pack. Incidentally, either component can be replaced separately. The light switch module also monitors the exterior lamps. If a bulb fails during operation, the LSM informs the driver via the instrument pack. Depending on the car's specification, this will be displayed either as a pictogram accompanied by a text message or by illuminating a warning lamp. Note that if a tail lamp fails, the light switch module illuminates the corresponding brake light at a reduced intensity, so that its brightness is equal to the remaining tail lamp. In the event of the LSM failing, the dipped beam and the tail lights are automatically switched on. The brake lights remain functional, and all remaining items controlled by the LSM will not function. If this occurs, the system is said to be in its emergency operation mode. Car telephones have become a popular accessory in recent years, and Rover 75 will be available with an integrated telephone. As you'd expect, the Rover 75 offers excellent stowage space. The glove box, larger than in any current Rover model, can house the CD auto changer and the handbook. Testbook is used extensively when working on the vehicle, and the new red diagnostic lead is connected here, in the driver's footwell. In addition, you'll need to use the dedicated Rover 75 compact disc whenever you're using Testbook. The complexity of vehicle wiring systems has grown considerably over recent years, with an increasing number of systems being operated by electronic control units. And the more wires and connections there are, the greater the chance of faults occurring. To minimize connection problems, the Rover 75 introduces a new electrical system called multiplexing. Multiplexing connects various systems together, forming a network of communication lines. These lines relay information between all the control units in the network, in much the same way as a telephone system works. A separate video looks at the new electrical system in more detail, but for now, here's a brief overview of the key points. Information, or data from sensors and switches, is converted into digital signals and relayed throughout the system network. So an ambient air temperature sensor, for example, only has to send its signal to the network, whereas previously it had to communicate with several control units individually. Data being relayed in this manner is referred to as a data bus system. The Rover 75 uses 3 bus systems that are linked together by the instrument pack. The 3 bus systems are called CAN bus, K-bus and diagnostic line, and are part of the main wiring harness. Within the instrument pack is a microprocessor that enables data to be transferred from one bus system to another. All the bus systems handle data extremely quickly. The CAN bus is the fastest and is used where rapid exchange of information is vital, for example in engine management or automatic transmission systems. The slightly slower K-bus connects all the body electronic systems together. It's primarily event-driven, in that messages are sent after a request has been made, for example switching on the lights or operating the sunroof. A new control unit, known as the GM6 body controller, is incorporated in the K-bus. It's located behind the glove box and is cream in colour. It controls the following systems: front window lift, alarm, low-line heater and air conditioning, interior lighting, wipers, heated rear window, central door locking, and, using Testbook, allows the vehicle to be set into or taken out of transit mode. If the car has electric rear windows, an alternative high-line GM6 is fitted. It's black and controls all the same systems as the cream-coloured low-line unit, but additionally controls the rear windows. Finally, as its name suggests, the diagnostic line is used by Testbook to communicate with each ECU for diagnostic purposes. The immobilization system used on the Rover 75 is similar to that used on the new BMW 3 Series and is referred to as EWS3. If a replacement key, ECU or lock set is required, They can only be ordered by Rover dealers via BMW's database in Dingolfing, Germany. Although the EWS3 system uses components of the locking and alarm system, it's a standalone immobilization system, comprising EWS3 immobilization ECU, located on the driver's A-post, engine control module, or ECM, GM6 body controller, key transponder, ring antenna, ignition switch, and instrument pack. On automatic vehicles, the inhibitor switch also forms part of the system. Each vehicle is supplied with 3 keys, and each key has 3 unique electronic identities or codes, namely an identification number, a password, and a rolling code which changes every time the car is started. When the ignition switch is turned on, the EWS ECU checks all 3 codes via the ring antenna and the transponder, and compares them to those held in its memory. If any of the codes fail to match, the car will remain immobilized. If the ECU confirms that a valid key is being used, the starter motor relay is energized, and a starting code signal is sent to the engine's ECM, allowing the engine to start. Once started, the EWS ECU cancels the rolling code from both its memory and the keys, and generates a new rolling code for future use. The starting code sent by the EWS ECU to the ECM is unique. During manufacture, the vehicle's ECM learns the signal it expects to receive for the rest of its working life. Hence, the EWS ECU and the ECM are effectively paired together, and this information is held in BMW's database. Therefore, swapping an EWS ECU or ECM from one vehicle to another is pointless, as the starting code won't match, and the vehicle will remain immobilized. When a replacement EWS ECU is delivered, it will contain the same data as the original. Once fitted to the car, it will need to be synchronized to the ECM using testbook. However, a replacement ECM is supplied in a newborn condition. Consequently, it needs to be matched to the existing EWS control unit in order that it can successfully receive the starting code. You'll need to use testbook to carry out this procedure, but note that you only have one chance to complete the operation. If a mistake is made, the ECM will lock up, and it will need to be returned to Rover Group. Any replacement keys are supplied ready to use, and the ECU can support up to 7 new keys in addition to the 3 keys supplied when the car is new. If the customer regularly loses their keys, they'll require a new control unit when they order their 11th key. Note that keys with remote handsets will require synchronizing to enable the remote locking and alarm functions. This is carried out using testbook. By the way, there's no emergency key access code facility with the Rover 75. The alarm and locking systems are controlled, as we mentioned earlier, by the GM6 body controller. The alarm is available with familiar functions such as volumetric protection and can be configured to suit various markets and customer preferences. A new feature is the optional battery backup siren, otherwise known as B-bus. It's active only when the alarm is armed and operates the siren via its own internal power supply, should the vehicle's battery be disconnected. Two stylish instrument packs are available. Customers can specify either the low-line or the high-line version. The only difference between the two being the method in which the information is displayed. The warning lamps in the upper part of the low-line unit are replaced on the Highline unit by a bicolour message centre. Within the instrument pack is a microprocessor that enables data to be transferred from one bus system to another. The microprocessor has a non-volatile memory for storing information such as the vehicle identification number, or VIN, service interval data, and the distance travelled, which is used for the odometer display. Resetting of the instrument pack's service interval indicator can be carried out using Testbook. As a backup, the light switch module also stores this information, and so if changing either the instrument pack or the LSM, the instructions in the workshop manual must be followed carefully. Whilst looking at the instrument pack, it's worth mentioning the new satellite navigation system. There are essentially two versions, the Highline and Lowline system. A separate video covers both systems in more detail. Incidentally, the Japanese market uses a different system altogether, which we won't study in this program. The main difference between the Highline and Lowline systems is their method of display. The Highline uses a 5-inch colour monitor, known as the board monitor, and incorporates the audio controls. It mutes the audio system while giving instructions to the driver via the front audio speakers. The Lowline version, on the other hand, uses a monochrome display in the Highline instrument pack and has its own dedicated loudspeaker. Maps of each country are entered into the computer via its CD-ROM drive. Each system can support 2 languages, although 6 are available. The 2 languages preferred by the customer can be configured at the dealership using Testbook. By using the Global Position System, or GPS, the computer receives data from at least 4 of the 24 satellites currently orbiting the Earth, and by using this data, it calculates the car's position. The GPS antenna is mounted on the parcel shelf and relays the satellite signals to the GPS receiver, which is mounted along with the computer in the luggage compartment. The system requires 2 more pieces of information in order to navigate. The first is the vehicle speed, provided by the ABS wheel speed sensors. And the second is the direction in which the vehicle is travelling, determined by a gyro compass incorporated in the satellite navigation computer. Note that due to limited space behind the board monitor, vehicles fitted with the Highline system have the radio tuner and video module located in the spare wheel well. Designed to work in conjunction with the primary restraint systems, such as the seat belts and collapsible steering column, the supplementary restraint systems of the Rover 75 easily meet the current and expected European, American and Japanese safety regulations. Let's take a brief look at the systems. Driver and passenger airbags are fitted as standard along with the new thorax airbags, fitted into both the front seats to protect occupants from side impacts. To complement the thorax bag, the optional side head impact protection bag protects the driver's or front passenger's head during a side impact. Unlike other airbags, it's designed to deflate slowly, giving prolonged protection, and on average takes about 5 or 6 seconds to deflate. All 5 seatbelts are 3-point inertia reel units and include pyrotechnic pre-tensioner devices. The deployment of the airbags and pre-tensioners is controlled by the Diagnostic and Control Unit, or DCU, located under the center console. It works in conjunction with the 2 side impact sensors fitted to the front seat cross members on each side of the car, and detects impacts from any horizontal direction around the vehicle. Depending upon the accident, the DCU only deploys the appropriate devices. For example, during a heavy rear impact, The front airbags will not deploy, although the seatbelt pretensioners will be activated. The Rover 75 will be available with a choice of 4 transverse engines, driving the front wheels via a new 5-speed manual Getrag or 5-speed automatic Jatco transmission. There are 3 petrol engines and 1 diesel. The familiar K1.8 petrol engine has been developed to improve performance. It now produces 88 kilowatts of power at 5,500 RPM and also meets year 2000 emission standards. The 2 other petrol engines are both derivatives of the KV6. One has a capacity of 2 litres, developing 110 kilowatts at 6,500 RPM, and the other has a capacity of 2.5 litres and produces 130 kilowatts at 6,500 RPM. The diesel engine is known as the M47R. It's a 2-litre 4-cylinder engine with 4 valves per cylinder. This engine uses the revolutionary Bosch common rail direct injection system and develops 85 kilowatts of power at 4,000 RPM. All engine management systems will be ECD3 compliant. ECD3 is the most recent European Commission directive regarding vehicle emissions, and it requires systems to have the ability to monitor components that affect emissions and to indicate which components may be at fault, such as the coolant temperature sensor. A separate video covers the engine options in more detail. The diagonally split braking system is servo-assisted and has reverse-vented front discs and solid rear discs. The rear disc brakes now incorporate drum units for the parking brake. Bosch ABS version 5.7 is fitted as standard on all Rover 75 vehicles. The 4 wheel speed sensors are new and are of the Hall effect type. The front sensors are mounted on the front hubs, while the rears are mounted on the inside face of the trailing arm. The new sensors are well protected from dirt and from being damaged. Electronic brake force distribution, or EBD for short, is also fitted as standard and is a function of the ABS system. It distributes the brake pressure between the front and rear axles, and its use means that a mechanical brake pressure conscious reducing valve for the rear axle is not required. EBD uses information from the ABS wheel speed sensors during braking to detect the variation in wheel speeds between axles. In response, it operates the ABS valves to limit the pressure reaching the appropriate axle, thereby optimizing brake pressure balance and hence vehicle stability. Remember that EBD apportions the brake pressure between the 2 axles, not to individual wheels. Therefore, in the event of one wheel tending to lock, it will be corrected by the ABS function and not by EBD. The EBD warning lamp is combined with that for the brake fluid level and handbrake. If the fluid level is correct and the handbrake is off, the lamp should light and then go out after a few seconds when the ignition is first switched on. In the event of the lamp remaining lit, or coming on while driving, it indicates that an EBD fault has occurred and the vehicle must not be driven. Optional electronic traction control is also available for vehicles fitted with the KV6 or M47R engines, and is yet another function of the ABS system. It prevents the front wheels from slipping during acceleration. By monitoring individual wheel speeds, the ABS control unit recognizes when one or both front wheels start to spin. In response, the traction control system initiates various actions to reduce the loss of traction, such as applying the brake momentarily to the spinning wheel. This action transfers torque to the wheel with the better grip. If both wheels are spinning, traction control can request, via the CAN bus, that the engine management system reduces engine torque. On diesel vehicles, the point of injection is retarded, whilst on petrol engines, torque is reduced by altering the ignition timing and/or the duration of injection. And additionally, on petrol engines, it can reduce the amount of air entering the engine via a secondary throttle unit. Incidentally, traction control will not operate if the brakes are applied. If required, for example when using snow chains, traction control can be disabled by the switch. However, on restarting, the traction control system will automatically be switched on, and each time the system carries out a self-check and illuminates the warning lamp for 4 seconds. If while driving a fault develops, the lamp will light and remain illuminated. If traction control is activated, the lamp will briefly illuminate to notify the driver. The Rover 75 has independent suspension front and rear, incorporating subframes. Power steering is fitted as standard, and the collapsible steering column is adjustable for both height and reach. The MacPherson strut front suspension uses forged aluminium lower arms, and when replacing the voided bushes, care must be taken to ensure they are fitted at the correct angle. By the way, the lower arms must never be used as a jacking point. Instead, jack up the car using the correct jacking points on the vehicle. The anti-roll bar uses ball joint links that help prevent bump steer. The bushes are specially developed to resist twisting and squeaking, and as a result, they should not be greased. The rear suspension is an adaptation for front-wheel drive of the BMW Z-axle, renowned for its excellent camber compensation. It comprises a multi-link system, dampers, coil springs, and a solid steel anti-roll bar. Like the front, the rear anti-roll bar bushes must not be greased. The steel lower control arm is marked to aid fitting. It's connected to the trailing link, which provides the toe adjustment via this bracket. The trailing link is, in turn, connected to the upper arm via press-fitted hollow ball joint. Adjusting the suspension geometry must always be carried out using Rover-approved wheel alignment equipment in order to maintain the integrity of the suspension system. Well, that concludes our look at this exciting new vehicle. We're sure you'll agree that it's a car with both style and substance.